Okay, so where we left off was finding our V total here. When you add these guys together, and when you do, you keep the negatives. So you're doing VA plus VB plus VC, but you're keeping these two negatives, okay? And so when you do, I think you get negative 2.12 times 10 to the 6 volts for your final answer. So that's number 49. The next one I asked you to do was number 53. Okay, and so for number 53, it tells you potential difference between X and Y is 12 volts, telling us between 2 points, so it's giving us a delta. Delta V is 12 volts. And it says a charge of 1 coulomb is released, so our Q is 1 coulomb, is released from the point of higher potential and allowed to move freely to the point of lower potential. How many joules of kinetic energy will it have? So we have 1 point here and 1 point here. The delta V between them is 12 volts. And as the charge moves, that's my Q, from this I can find my delta EQ. My delta EQ, because remember V is equal to EQ over Q. So delta EQ should just be equal to V times delta, Q times delta V. So delta EQ should be equal to 12 volts times 1 coulomb, which will be 12 joules. So that's the change in electric potential energy. So right now, if I release it and it moves, it means it had 12 joules of electric potential energy here, and now when I release it, it moves to this point, losing the 12 joules of electric potential energy as it turns into kinetic. So the question wants to know how much kinetic energy will it end up having when it does that? That'll be 12 joules because it all switches. How many joules of kinetic energy will it have? It all switches over. Okay, that's number 33. Number 35 was the next one. And number 35 says if 6.2 times 10 to the negative fourth joules of work, so work done, and remember work done is equal to change in energy, and in this case it's going to be potential, electric potential, are required to move a charge of 3.2 nanocoulombs. So Q equals 3.2 times 10 to the negative 9 coulombs. From a point B to a point A in an electric field. What is the difference? So from B, it's going from B to A, and you are doing the work, and it wants to know what's the delta V. Well, we have the delta EQ, we have the Q, we can find the V. Because if V is equal to EQ over Q, then delta V is equal to delta EQ over Q. So we have 6.2 to the negative fourth joules over 3.2 times 10 to the negative 9 coulombs. Yeah, it's negative 4. Sorry, I was just making sure. It would have been nice if that had been 6.2 because it would have divided evenly. And so when you do this, you get a delta V of 193,750 volts. Okay, that's a 3, even though it looks like a 5. Yeah, that didn't help at all. So that's part A. Part B wants to know how much work would have been required to move 6.4 nanocoulombs of charge. If I double the amount of charge, then how much work am I going to need to do to move it across the same potential difference? If this gets bigger and delta V stays the same, the EQ should have to double, right? Because we know EQ is just going to be equal to Q delta V. So if delta V isn't changing, because it says we're moving it across the same potential difference, and Q is doubling, EQ should double. So it should end up being just 6.2 to the negative fourth doubled. So what is that? 1.24 times 10 to the negative 3 joules. And the last part of this question says, which point is higher electric potential difference? We had to do work to move it to A, so A must be higher. If it had gone on its own, it would mean that B was higher. But we did work to move it to A, so A must be higher. All right, you have one more. It's number 56, and it's exactly like number 46. Okay, so it's two charges, some distance apart, and it tells us there's 6 and negative 3. So 6 microcoulombs, negative 3 microcoulombs. And it tells us the distance is 8 centimeters. It's going to be closer to this one, so R1 and R2 will be 8 centimeters minus R1. And in this question, it wants the two positions. So the total potential difference is 0. So it'll be KQ1 over R1 equals negative KQ2 over R2. The K's cancel. Q1 over R1 will equal negative Q2 over 8 centimeters minus R1. So 8 centimeters minus R1 times Q1, and on this side, negative Q2 R1. So Q1 8 centimeters minus Q1 R1 is equal to negative Q2 R1. Take the Q1 R1 over, it becomes positive. So Q1 R1 minus Q2 R1, factor out the R1, Q1 minus Q2. And then to get the R1 alone, divide. So Q1 times 8 centimeters divided by Q1 minus Q2. So Q1, I'm calling this one number 1, this one number 2. So 6 microcoulombs times 8 centimeters divided by 6 microcoulombs minus a minus 3. On the top, 48. On the bottom, positive 9. 48 divided by positive 9 should be 3 repeating meters. And so R2 is 8 centimeters minus that. So that's what? 2.6 repeating. This one is towards number 2, and this one is toward number 1. Okay, that's the first one. Second one, on the side of the one that's smaller in magnitude, which is the 3, so it's going to be a point out here. So we could call this distance x. That will be R2. And so R1 will be 8 centimeters plus x. Again, V1 plus V2 should equal 0. So KQ1 over R1 will equal negative KQ2 over R2. The K's cancel. It becomes Q1 over R1, Q1 over 8 centimeters plus x will equal negative Q2 over x. Cross multiply. Q1x is equal to negative Q2 times 8 centimeters plus x. Multiply through. Q1x is equal to negative Q2 times 8 centimeters minus Q2 times x. Bring that over. Q1x plus Q2x is equal to negative 2 times 8 centimeters. Pull out the x, Q1 plus Q2, and divide. And so we'll have x is equal to negative Q2 times 8 centimeters over Q1 plus Q2. Fill in your values. Negative 3. So that'll be a positive. Times 8 centimeters. That'll be 24. And on the bottom, 6 microcoulombs plus a minus 3. So 24 over 3. X is 8 centimeters. So that's R2. That means R1 is 8 plus 8, or 16 centimeters. Okay, and so we have, this is opposite side as number 1, and this one is towards number 2. All right, so there are all your homework questions. Hopefully they went well for you. If something here doesn't make sense, just put a message in the group and I'll try to explain. Okay, good.